So in the previous video, we had stopped at the receiver schematics. We had just discussed the receivers. In fact, I had just given the schematics and I didn't complete the explanation. So I will we will start with a brief discussion of the schematics and how the receiver schematics work, or how the receiver works. We'll try to understand through the schematics. So we have the we know that in general the received signal in QPSK will be root ES. So I am writing the expanded form which we obtained by using the trigonometric identity cos A plus B minus root ES. So one thing which I missed here is root 2 by Ts cos 2 pi of Ct minus root Es sine 2m plus 1 pi by 4 root 2 by Ts sine 2 pi of Ct, and of course small t is 0 to Ts. I will not be writing it often. Ts is the symbol duration, Es is the symbol energy. And of course with this is one of a sample received signal, and this will be corrupted by the noise, additive white Gaussian noise of two-sided power spectral density n naught by 2. A sample function can be expressed like this. Now in the, if you recall that figure, in the received signal splits into two, and in the top arm it is getting multiplied by root of 2 by Ts cos 2 pi of Ct. In the top arm it is getting multiplied by this, and in the bottom lower arm it is getting multiplied by root of 2 by Ts sine 2 pi of Ct. So and of course after getting multiplied by these basis functions, that is in the top arm this is the one which gets multiplied with this, or this gets multiplied with this, and in the lower arm this is multiplied by root of 2 by Ts sine 2 pi of Ct, if you recall the figure. And after multiplication result is passed through an integrator wherein you integrate from 0 to Ts, and you consequently, when you sample the output of the integrator at the end of the integration interval which is shown as Ts, you get the random variable R1 in the top arm and R2 in the lower arm. So R1 will be, you are going to multiply this with root of 2 by Ts cos 2 pi of Ct and integrate from 0 to Ts. So we have done such integration a lot of times before, so I will not do it specifically here. I will not do it explicitly here, but I will give you the result by explaining the steps. So RT into this, integrate from 0 to Ts, and let's see what happens. What you're going to get is root Es cos 2m plus 1 pi by 4 will come out of the integration because it's not a function of time. So I can write R1 is equal to, and before I proceed, let me emphasize here that I am ignoring for the moment I am ignoring the power splitting which happens, because when the received signal is split into two, if you recall the schematics, the received signal is split into two. I am for the moment neglecting the power splitting that happens, and if required we will revert later and see what happens when we take into account the power splitting, or maybe I will give that as an assignment to you. You can do that later. So I am going to proceed here with the assumption that there is no power splitting. I am going to ignore the power splitting that happens when you bifurcate the signal into two, because it's possible to compensate that in many different ways anyhow, and I'll leave it to you as an assignment to find out. So R1 is equal to, this is multiplied by root of 2 by Ts cos 2 pi of Ct and then integrated from 0 to Ts and sampled. So you get, as I said, root Es cos 2m plus 1 pi by 4, and of course this into this you will get, when you multiply these two and integrate from 0 to Ts, you will get the result as 1, because as you know this is of unit energy, so you're simply multiplying the two and integrating over 0 to Ts, you'll get the result as 1, because you'll get the norm, the energy of the signal, which is 1, because this and this form orthonormal. And due to the same reason, when you multiply this with this and integrate from 0 to Ts, since these are orthonormal, the result will be 0. So other than this, the next contribution that's going to come is from this, the noise sample function. So nt into this, you integrate from 0 to Ts, you will get a random variable n1, which may take a sample value which is as given by small n1. So this will be 0 mean and variance n0 by 2. So that is how it is. If we had considered the splitting of the power, then the variance would have been less than n0 by 2. You have to find out what would have been the variance if we consider the splitting. And also this would have been less than what we have here. Again, you find out what that would have been if we had considered the splitting of the power into 2. The splitting of the signal into 2 parts at the front end of the receiver schematics. And by similar arguments, you can show that in the lower arm, R2 is going to be minus root es sine 2m plus 1 pi by 4 plus n2, where n2 is also 0 mean and variance n0 by 2. n1 and n2 will be independent of each other, but they will be identically distributed with 0 mean and variance n0 by 2, Gaussian of course. So this is what we will get as R1 and R2, and in the absence of noise you can see that R1 and R2 explicitly give the coordinate of the signal point on the signal space diagram on the constellation. So for example, if signal S0T was transmitted, M would have been 0 and R1 and R2 would have been root ES cos pi by 4, which will be nothing but root ES by 2, and R2 would have been minus square root of ES by 2, the whole under root. So ES by 2 under root. Again M0 we are assuming, then sine pi by 4 becomes 1 by root 2. So you would have got this as R1 and R2 if noise were not there. And this clearly gives you the coordinates of the signal point corresponding to the point corresponding to the signal S0 in the signal space. And if you recall, in the signal space, S0 is here, and that's exactly what we get. R1 is ES by 2 under root, R2 is minus root ES by 2. But in the presence of noise, what happens is you will end up making a mistake occasionally, and the next task is to find out what is the probability of the receiver making an error in correctly deciding which was the transmitted signal, or indirectly making an error in detecting the transmitted symbol, because as you know, symbol is mapped onto the signal. So let's move on to that now. So let's find out what is the probability that the receiver makes an error in detecting the transmitted symbol or signal correctly. So the error results because of this. Otherwise, it gives exact the coordinates, and there is you'll always end up getting the detecting the correct the symbol correctly. So let's find out what happens. Now, before we proceed, in one of the earlier videos we had discussed that the optimum decision rule can be mapped onto the signal space, and it's possible to divide the signal space into regions corresponding to the hypothesis, or in this case corresponding to the symbol transmitted. And we can do the same thing here for QPSK. Let me draw the signal space and the constellation. So we have S naught here, S1 is here, S2 is here, and S3 is here. And of course, I have written it like this. We have written it as in the form of a vector because now the signal has become the vector when you map it, when you show it in the signal space. Anyhow, now whenever you receive, having received R1 and R2, the optimum decision rule, we have discussed this earlier. I'm just quickly going to recollect it. Having received R1 and R2, we locate the point described by R1 and R2 on the signal space, and whichever signal point is closest to that, we are going to declare that as the transmitted signal. This is how the optimum decision rule works when you see it on the signal space. And let me reiterate, this type of a mapping of decision rule onto signal space, the way we have mapped it here, in that when I say that having received R1 and R2, we locate the point in the signal space, and the signal point closest to that point is declared as the transmitted signal. This way the optimum decision rule works only when the additive noise is Gaussian. Okay, since in the type of digital communication system that we discussed, the additive noise is always Gaussian, this type of an approach works. Okay, so the optimum decision rule, again, I'll repeat that again. Having received R1 and R2, we locate the point in the signal space, and the signal point closest to the closest to the point described by R1 and R2 is declared as the transmitted signal. So that way, it's possible to divide this signal space into 4 regions. It is possible to divide the signal space into 4 regions. So I will shade it in different ways. Now this region, that is this quadrant, all the points in this quadrant are closer to S0 than other signal points. So we can declare this region to belong to the signal S0T, in the sense, if we determine R1, R2, and if the point identified by R1, R2 lies anywhere in this quadrant, you can see that that point is closer to this than the other 3. So whenever R1, R2 described a point which lies in this quadrant, we can say that S0 is the transmitted signal, S0T is the transmitted signal, or equivalently we can see that the transmitted symbol corresponds to the signal S0T. Similarly, you can see in this quadrant, all the points are closer to S3T. In this quadrant, all the points are closer to S1T. And in this quadrant, all the points are closer to S2T. So, say you determine, you get R1, R2, you don't know what is the transmitted symbol, you just see where R1, R2, where is the point described by R1, R2 lie. Let's say it lies somewhere here. Then your decision will be the transmitted symbol was the one corresponding to the signal S3T, or equivalently the transmitted signal was S3T. You may be right, you may be wrong, but most of the times you will be right, because the decision rule is optimum. Occasionally you will go wrong, and what we are going to find out now is the probability of the receiver going wrong in taking a decision when it follows this type of a decision rule, which is optimum in the given circumstances. So let's find out what is the probability of error. So what we do is, again, as we did with aryFSK, we will first find out what is the probability of correct reception of a symbol, correct detection of a symbol, and then we will subtract that from 1 to get the probability of error in detection of that symbol. And since the whole case is symmetric and the 4 symbols are equiprobable, the average probability of symbol error will be the same as the probability of an error in detecting any of these 4 symbols as any of these four symbols wrongly. So what we will do is we will take the signal S3T or the symbol corresponding to signal S3T as the transmitted symbol or signal for the time being to begin with. So let's say that this is transmitted. The receiver doesn't know. Of course, we are trying to find out the probability of, first we'll find the probability of the receiver detecting this correctly. Let's say this is transmitted. So transmitted signal is S3T, or the symbol corresponding to S3T was the output symbol, and that means M is equal to 3. When M is equal to 3, you note here that this becomes cos 7 pi by 4. And here when M is equal to 3, of course, it is the same as 2M plus 1 here. So this becomes sine 7 pi by 4. This becomes sine 7 pi by 4. Now, cos 7 pi by 4 is equal to 1 by root 2. Cos 7 pi by 4 is equal to 1 by root 2. So you will get the result as root es by 2, the whole under root es by 2 plus n1, and sine 7 pi by 4 will be minus 1 by root 2. So minus root es minus 1 by root 2, the result will be es by root 2. So that's exactly this point. So if it's only these two, then we see that we exactly get this point. But this is going to create problem for us. So now, with the assumption that S3T was transmitted, under the assumption that S3T was transmitted, we see that we are receiving this. So now we can write down, remember N1 and N2 are identical Gaussian distributed, mean 0, variance N0 by 2. I have not considered the power splitting that happens due to the bifurcation. I am leaving that as an exercise for you. You consider the power splitting to happen and rework and see whether the results are the same. That's an assignment for you. So we can now formulate, we can write the expression for PR1 given S3. So I'll write like this, given S3 was transmitted, that is the conditional density function of the random variable R1, the one which you get in the top arm of the receiver schematic, given that S3 was the transmitted symbol, is 1 by root pi n naught. It is root of 2 pi into sigma. Sigma is root of n naught by 2. So the 2 in the denominator of n naught, and this root 2 gets cancelled. E power minus R1 minus root es by 2 whole square by n naught. 2 sigma square is 2 into n naught by 2, so it becomes n naught. And P R2 given S3, that is given the transmitted signal was S3, is equal to 1 by root pi n naught. It will be exactly the same as this. The only difference is that in place of R1 we will have R2. But note that R1 and R2 are statistically independent. They are both Gaussian distributed with mean root es by 2 and variance n naught by 2. Both having a mean root es by 2 and variance n naught by 2. And they are identically distributed. So now the signal S3T or the symbol corresponding to the signal S3T is detected correctly if the points described by R1, R2 lie in this quadrant. That means the signal S3T or the symbol corresponding to the signal S3T is detected correctly if and only if both R1 as well as R2 are positive. They should both simultaneously take a value greater than 0. Only then you will lie in this quadrant, and whenever you are in this quadrant, you are going to declare that the transmitted symbol is S3T. So to detect S3T correctly, having transmitted S3T, to detect it correctly, your R1 as well as R2 should both be greater than 0. R1 should take a value greater than 0, R2 should take a value greater than 0. Only then you are going to land in this quadrant. So probability of correct detection is when both R1 and R2 take a value greater than 0. So let's find out what is the probability of that. Once we find the probability of that, we'll get the probability of correct detection of signal S3T or the symbol corresponding to signal S3T, and when we subtract that from 1, we'll get the probability of error in detecting that particular symbol or signal. So probability of R1 becoming greater than 0 is simply the integral of this from 0 to infinity. Isn't it? You just have to integrate it from 0 to infinity. This gives you the probability of R1 being greater than 0. And similarly, the probability of R2 being greater than 0 will be an integral of this from 0 to infinity. And you can see that since R1 and R2 are dummy variables, they are just variables of integration. Since they are just variables of integration, since they are just dummy variables, you can see that this result will be the same because the distributions are identical. The result will be the same. So if you evaluate one, that is enough. The result will be the same as this. So now, if S3T has to be detected correctly, the probability of S3T being detected correctly is that, I repeat, both R1 and R2 has to be greater than 0. Probability of R1 being greater than 0 is this. Probability of R2 being greater than 0 is this, which incidentally happens to be the same as this. So probability of both R1 and R2 being greater than 0 will be the product of these two, which simply means that the probability of R1 as well as R2 being greater than 0 will be simply this raised to the power 2, because what we had here, the numerical result which you get will be the same as what you would get for this. So when you multiply, it is the same as raising the whole thing to the power of 2. And you don't need an identifying subscript here because it's just a variable of, it's just a variable, it's just a dummy variable. You're going to integrate it and you have limits 0 to infinity. Now this gives you the probability of S3T being detected correctly. This gives the probability of S3T being detected correctly, which means that 1 minus this will give us the probability of an error in detecting S3T. Now before that, let's substitute for this. Let's say this is equal to u. We will bring it in q in terms of q function. Let's make this substitution so that dr is equal to root n0 by 2 du, and when you make the substitution here, you will get 1 by root of 2 pi. Lower limit becomes minus root es by 2 divided by root n0 by 2. So when you put r0, you get minus root es by 2 root n0 by 2, which is the same as minus root es by n0, the whole. es by n naught under root with a negative sign. And of course upper limit remains as infinity, because if you make this infinity, u is infinity. And e power minus u square by 2 du. You can see that when you square this, you get r minus root es by 2 whole square divided by n naught by 2. That 1 by 2, you come here, you get u by 2. So rather u square by 2, and hence you have it like this. And this before we it's almost in the Q function form, but there is one small tweaking required. You see that this is actually 1 by root of 2 pi e power minus u square by 2 is nothing but a distribution of a zero mean Gaussian random variable of mean 0 and variance 1. And you are integrating this from minus, so this is 0, so some minus root es by n naught to infinity. In fact, to infinity. This is the area which you are calculating here. Now that will be the same as 1 minus this area. So if you from 1, if you subtract this area, 1 is the total area under the distribution density function. From 1, if you subtract this area, you will get this area, which is the same as this area. So which means that we can write this as equal to 1 minus, we can write this as equal to 1 minus 1 by root 2 pi root es by n naught to infinity e power minus u square by 2 du. And now we recognize the second term here. We recognize the second term here as the Q function. So I can write 1 minus Q root es by n naught, and there was a whole square which I have missed out, so whole square. This is the probability of correct detection of the signal S3T or the symbol corresponding to the signal S3T. And 1 minus this will give us the probability of error in detecting the signal S3T. So 1 minus this, let me square this now. So 1 minus 1 plus Q root es by n naught square. So it is just a minus b whole square. So 1 square of this plus square of this minus 2 into Q root es by n naught. And when you open this bracket and expand it, there's nothing much to expand, you just have to open the bracket and take care of this negative sign. You will get 1 minus 1 and minus of this and plus of this. So this will be equal to 2q root es by n naught minus q root es by n naught whole square. And this is the probability of error. Because if you recall, we found out first what is the probability of the signal S3T being detected correctly, and then we got that as this, to be precise, and we just subtracted it from 1 because S3T can be either detected as S3T itself or something else. So having found out the probability of correct detection of S3T, we just subtract it from 1 to get the probability of error in detecting the signal S3T, or equivalently the symbol which is mapped down to the signal S3T. And as I said, since if you calculate the, you can do that if you want. If you try to find out what's the probability of symbol S2T being detected correctly, you'll end up getting being detected wrongly, you'll end up getting exactly this expression. If you try to find out what's the probability of S0T being detected wrongly, you'll end up getting exactly this expression. So this being the probability of error in detecting any of the four symbols, and the four symbols being equiprobable, unless otherwise stated in a digital communication system, the symbols will be equiprobable. So probability of the receiver out, the transmitter output being S0T or S1T or S2T or S3T are all 1 by 4. So that being the case, the probability of error in, the average probability of error in detecting a symbol in a QPSK receiver which employs coherent detection and which employs an optimum decision rule is this. This is the probability of error for a symbol, probability of symbol error in coherent QPSK receivers, and we can approximate this as equal to 2Q root Es by n naught. We can approximate it as 2Q root Es by n naught, because if you see here, this is Q of something to the power 2. So if the signal energy is strong, if the signal is sufficiently strong compared to the noise power, then this will be a small number. And when you raise it to the power 2, it will become even smaller. This will be a number less than 1. When you raise it to the power 2, it will become even smaller. And that is being subtracted from this, which is 2 times this. So 2 times this, from that you are subtracting the square of this. So the major contribution to this will be from this. The major contribution to this will be from this, especially when Es by n naught is large. That means when the signal energy is, the signal is very much strong when compared to the noise power. So we can conclude this now by saying that the probability of symbol error in QPSK is approximately this, and to be more specific, it is this. When Es by n naught is huge, we can, very large, we can neglect this and approximate it to this. Now, before we move on to the next higher level modulation scheme, we have to quickly take a look at two examples. This is the right time to discuss these two examples. The first example which I am about to discuss now is actually an extension of the performance evaluation which we carried out a short while ago. The performance evaluation of QPSK which we carried out a short while ago. So in this example, this is an extension, and this example will also give us an idea as to how the bits have to be mapped onto the symbols. So please recollect that QPSK, in QPSK there are 4 symbols, and these 4 symbols are represented by 4 different signals which are different in the sense their phases are different, and this we have discussed earlier. So there are 4 symbols, and these 4 symbols are made up by combining 2 bits. So you have 0 0 0 1 1 0 and 1 1. So now this example which we are about to discuss will give us an idea how to map the group of 2 bits which we will hereafter call as die bit. How to map the die bit onto the symbols, that we will come to know once we understand this discussion which I am going to present in the form of an example. So what I mean when I say how we map this die bits onto the symbols is that we know that the signal space and the constellation of QPSK is like this. We have the signal S0T here, S1T, S2T and S3T. So we have the 4 possible combinations with the die bits. So it may appear that we can map the die bits, say like this, or any other random way we feel like, but actually when we solve this example we will see that it is there is a particular way in which it has to be done so that we can minimize the bit errors, minimize the errors that happen in the bits. Okay, so when we discuss the example it will become clearer. Now the example is this. The example that, in fact, as I said, this is actually an extension of the performance evaluation, and I'm going to present it as an example. So the question is, in fact, the analysis that we are going to conduct now is, we have to find out what is the probability that, say, the signal S3T is being detected as S0T or S2T, and S3T being detected as S1T. So the signal space, again, if I quickly draw here, we have the signals, we have the signal space like this, and the question is, what is the probability that S3T, or the symbol which is mapped onto the signal S3T, is detected as either S0T or S2T? That is, of course, from symmetry we know that the probability of that will be the same. Or what is the probability of S3T being detected as S1T? So what we do is we'll first find out what is the probability that S3T is being detected as S0T. Let's see what is the probability that S3T is being detected as S0T. So from the previous discussion we have with us the conditional density functions. I'll just rewrite it quickly here. And so writing it down so that there is a continuity in the discussion. So these are the two density functions we have. Now the probability of S3T being detected as S0T, which we will first find out, is the probability that R1 is greater than 0. If you recall from the signal space diagram, so this is S3T, and we have S0T here in this quadrant. So if S3T has to be detected as S0T, R1 has to be greater than 0 and R2 has to be less than 0. So R1 has to be greater than 0 and R2 has to be less than 0. So the probability of R1 being greater than 0 and R2 being less than 0 gives us the probability that S3T will be detected as S0T. So let's evaluate that. We have the density functions here. With the help of these density functions, we can easily evaluate what is the probability of this happening. R1 has to be greater than 0 and R2 has to be less than 0. Right. So R1 has to be greater than 0 and that probability will be greater than 0. So we have to integrate the density function from 0 to infinity. This is the probability of R1 being greater than 0, and simultaneously R2 has to be less than 0. So R1 and R2 being independent, statistically independent, they are, recall that they are both Gaussian and they are independent. So the probability of R2 being less than 0 is an integration of the R2's conditional density function from minus infinity to 0. And this, as you know, we can write as equal to, because the entire integration from minus infinity to plus infinity will give us 1. So we can write this as 1 minus 0 to infinity. We can write it as 1 minus 0 to infinity. And we now multiply these two terms. We open up the brackets. So if basically you have this into this, so we open up the brackets. And before I open up the brackets, let me let me say that R1 and R2 are just variables of integration. They are dummy variables. So if you just write like this, the result remains unchanged. The result remains unchanged. Now if I open the brackets, what happens is I will get, so 1 into this, I get the same as this, minus, so this is 1 into this, and minus this into this, we will get 1 by root pi n naught 0 to infinity e power minus r minus root es by 2 whole square by n naught tr. So and of course this to the power 2. So when we open up the bracket, this into this, we get this, and this into this, you will get the square. It's the same thing. It basically is the same thing. So you get the same as this to the power 2. Now we can make appropriate substitutions. You can make appropriate substitutions, which I will not show the steps here. You can make appropriate substitutions and write this in terms of the Q functions. I leave it as an assignment for you. What is the missing steps? What are the missing steps? You fill them out. So I can express this in terms of Q functions like this. You can write it like this. And of course, we can expand this and write it as 1 minus q root es by n naught minus, so we square this, 1 minus q root es by n naught square. So it is 1 plus square of this, the negative sign makes it minus 1, and minus square of this, and then we have minus 2 into 1 into q, that the negative sign make it plus 2q root es by n naught, and we see that this gets cancelled, and this and one of this will get cancelled because there are two here and there is one negative here, so that gives us the final result will be q root es by n naught minus q root es by n naught whole square. So this is the probability that S3T will be wrongly detected as S0T, or we can say equivalently, I have been telling this every now and then, the symbol mapped onto S3T is being erroneously detected as the symbol which is mapped onto S0T. This is the probability of that happening. So we will write down this as equal to, so we will write that in the form of a compact notation, probability of S3T being detected as S0T. That's what I mean by this shorthand notation. Probability of S3T being detected as S0T is this. Now from the symmetry, from the symmetry of the signal space, which I will just quickly draw here again. This is S3, S0, S2, S1. So S3T being detected as S0T, the probability is this. Now S3T being detected as S2T, the probability will be the same because you can see the symmetry, right? So even if you calculate again, you'll see that you'll end up getting the same result. So you can even see it from the symmetry. S3T being detected as S0T, the probability of that happening will be the same as the probability of S3T being detected as S0T, S2T, sorry. So that means this will be the same as this. S3T being detected as S2T will be the same as S3T being detected as S0T, which means that the probability of S3T being detected as either S0T or S2T will be the union of the two probabilities. Because either S0T or S2T, both will not happen. So you either detect it as S0T or S2T. The probability of S3T being detected as S2T or S0T will be the sum of these two. The sum of these two in the sense twice this. That will be 2q root es by n naught minus 2q root es by n naught square. This will be the probability of the symbol S3T being detected as either S0T or S2T. Yeah. Now, from this we can, so remember this result, and from this we can also find out what is the probability of S3T being detected at S1T. What is the probability of S3T being detected as S1T? That can also be found out from this, because see, if you have S3T, you either detect it as S. So if you have S3T and you are calculating the probability of S3T being detected as this or this. Now if you know the probability of the error, if you know the probability of the error, we have already calculated the probability of error, which I will just quickly write here in the at the end of the previous discussion. Before we started discussing this example, we had derived the expression for the probability of error. I will just write it here. The probability of error in QPSK is this: 2q root es by n naught minus q root es by n naught whole square. This we had derived, and we have this as the probability of S3T being detected as either this or this. So from the an error happens when S3T is detected as either S2, S0 or S1, which means that the probability of S3T being detected as either S2, S3, S2, S1 or S0 is this. Because when S3T is detected as any of these three, you have committed an error, and the probability of that is this. So if we subtract from this the probability of S3T being detected as either S2T or S0T, we should get the probability of S3T being detected as S1T. So I will write here probability of S3T being detected as S1T is equal to this minus this. So from this we have to subtract this. Let's subtract it. It's from this, when we subtract this, remember from this we are going to subtract this. What happens is this will vanish. And remember, from this you are subtracting this. So this will get multiplied by a negative sign and will get added to this. The result will be 2 times this minus once this, and that will give you simply this. So this is the probability of S3T being detected as S1T. This is the probability of S3T being detected as S1T. So what we see here is that, what we can clearly see here is that straight away we can see, without even much of a discussion, we can see that this will be more, this probability will be more than this probability, because if you see this it can also be seen from the signal space, but I'll come to it later. If you take a close look at this, you see that, as I said at the towards the end of the discussion, before we started this example, this will be a number which will be generally small. It will be definitely, it will be less than 1, and if the signal energy is more than the noise energy, this q will be a small number, and you are actually squaring it here. And over here what you do is you have a number which will be considerably large compared to this, and from that you are subtracting a number which is very small compared to this, which means that this will be approximately equal to, this will be approximately equal to 2q root es by n naught, or this result will be dominated by this, and you can clearly see that this is going to be much smaller than this. This is going to be much smaller than this, which means that probability of S3T being detected as S0T or S2T will be much more compared to the probability of S3T being detected as S1T. And it can also be intuitively felt from the signal space, because this distance is more, because you see you are going to declare the signal as S1T whenever you land in this quadrant. So from the signal point S3T, you can see that this quadrant is farther than these two quadrants. Remember, this was root ES, so this is 2 root ES, and this was root 2 ES. So you can see that this distance is definitely much smaller than this. So this symbol being mistaken as either this or this will be, the probability of that will be more. The chances of that will be more compared to the chance of detecting this as this. So that is the lesson we learned from this analysis, and that is clearly visible here. Probability of S3T being detected as S1T is this. S3T being detected as either S2T or S0T is this, which is smaller, or rather which is larger than this. This is small, this is smaller than this. So this probability is smaller. S3T being detected as S1T, that probability is smaller, which means that when you look at a QPSK system and when you look at the errors that are going to happen. And of course, this again, due to similarity, we can say that probability of S2T being detected as this or this will be more than the probability of S2T being detected as this. Similarly, for S0T, it being detected as this or this is going to be more probable than it being detected as this. So when you look at the errors that happens in a QPSK signal as and when it is received, you will see that the errors will be dominated by such errors where the signals are detected as the ones which are lying closer to them than the ones which are lying farther. Which means that when you translate in terms of symbol error, the probability of symbol errors will be dominated by such symbol errors where a symbol is detected erroneously as the one which is mapped onto the signal adjacent to the signal on which that symbol is mapped. Now that gives us an idea as to how the die bits have to be mapped onto the symbols. Now what happens is, this discussion tells us how the die bits, remember die bit is a combination of two bits, I mentioned that in the beginning. We have the signal space like this. We have the signal space like this, and suppose we map the die bits like this. Let's say we map the die bits like this. See, I will draw it here. S0, that is signal S0T, S1, S2, S3. I have the four signals, and suppose we map the die bits like this. Suppose we map it like this. So we have 0 0, this point corresponds to 0 0, this point corresponds to 0 1, this corresponds to 1 0, and this corresponds to 1 1. Now what happens is, what happens now is that you know clearly that probability of, I'll concentrate on this, probability of S3T being detected as S0T is more than the probability of S3T being detected as S1T. Now what happens when S3T is detected as S0T? You are going to detect 1 1 as 0 0. That means you are losing 2 bits. So 1 1, if you detect as 0 0, you are losing 2 bits. This one is detected as 0, this one is also detected as 0. What happens if S3T is detected as S1T? You can see that you lose only 1 bit. The first one is erroneously detected as 0, but the second one you detect correctly. Now this means that since this probability is smaller, the probability of S3T being detected as S1T is smaller, it is advisable to do the mapping this way. It is advisable to do the mapping this way. Probably I will, instead of overwriting, I will do it properly so that it becomes clearer. So it is advisable to do the mapping this way. 0 0 0 1, otherwise I have to overwrite and then again come back to this 1 1 1 0. So we do the mapping this way. Now what is the advantage? What happens when we map like this? Again, if S3T is detected as S0T, which is the dominant type of error, you're losing only 1 bit. You're losing only this one. The second 0 you detect correctly. If S3T is detected as S2T, the other dominant error event, you see that you are losing only the second bit. The second 0 is detected as 1. Now, if S3T is going to be detected as S1T, which is a rarer event compared to the previous two, you are going to lose both the bits. So the chances of losing both the bits we are able to bring down, because this event is of lesser probability, whereas these two events are of higher probability. So if we map the symbols like this, the die bit like this, if we map the die bits onto the signals or the symbols like this, we will be able to bring down the probability of bit error rate, though the probability of symbol error remains the same. The probability of bit error rate can be brought down if we map it like this. Again, I repeat, if this happens, which is a rare event, you are losing 2 bits. If this happens, which is an event which is going to be more frequent compared to this, you lose only 1 bit. So this is the better way of mapping the symbols. And this, as you know, if I write it down here adjacent to this, if I write it down here adjacent to this, you note that S0 remains as 0, 0, S0 remains as 0, 0, S1 remains as 0, 1, S1 remains as 0, 1, S2 becomes 1, 1, S2 becomes 1, 1, running out of ink, S2 becomes 1, 1, and S3 becomes 1, 0. So excuse me for that, I am running out of ink. So S3 becomes 1, 0. So this type of coding you know already. It's called as the gray encoding method. It's called as the gray encoding method. So you should have studied it in basic digital systems. So we always go for this type of a gray encoding when we map. So we can write here, this is for M0, this is for M1, this is for the symbol corresponding to M0, symbol corresponding to M1, symbol corresponding to M2, symbol corresponding to M3. So always remember this picture, that is, you have the symbol, and the symbol error rate is something that you don't have much of a control over. But if you map the bits onto the symbols in such a way that you end up losing less number of bits for more probable error events, and you lose relatively more amount of bits for the lesser probable error events. So the example is over here. So this is of a lesser probability, you lose 2 bits. This is more probable, you lose only 1 bit. So this way you can bring down the bit error rate, the average bit error rate. So that's the point of this example. And before I take the next example, and probably that will happen in the next video, I would just like to mention here that here onwards we will be referring to, because we will be referring to the higher levels of phase shift keying later. This is the QPSK. Next we'll go for the next higher level, which will be the octal PSK. So here onwards we will be referring to phi 1t. Here onwards we will be referring to phi 1t as, of course, you know what is phi 1t, root 2 by ts cos 2 pi fct. We will be referring to this as the in phase carrier component, and phi 2t, which is root of 2 by ts sine 2 pi fct, as the quadrature carrier component. In phase and quadrature, quadrature phase component. That means in the further discussions we will simply refer to this axis as I, which means that it is the in phase, which means that it is the in phase quadrature component. Again, forgive me, I am running out of ink. We refer to this as the in phase, the I axis, and we will refer to this as the quadrature. The vertical axis will be referred to as the quadrature axis, Q. So I, Q. Here onwards we will be referring to the two axes like this. So just wanted to introduce that also at towards the end of this discussion of this example. So we'll take one more example, but probably that will be in the next video.